Good morning, good afternoon, good evening, depending on where you're joining in from. I'm a very warm welcome to all of you in today's webinar brought to you from Swift Kanban and Digite. The subject of today's webinar is lead time, what we know about it, and how we use it. Let me go ahead and get started right away. So we'll start off with a brief introduction to our main speaker today, and I will give you a quick overview of Digite Swift Kanban, and then hand over the presentation, for the main presentation, and then finally we will hopefully have a good audience Q&A session where we should be able to answer questions that you have on the presentation today, as well as the general implementation questions that you might have on Kanban. So some quick housekeeping. We will take questions via the Q&A box that you should see on the right side of your screens. We'll, depending on the number of questions we get, we'll try and group questions by topic, and in general take them in the order received. And so that the webinar is being recorded, and the slides and the recording will be made available after the meeting. So with that, let me go ahead with the introductions. I'm very happy to introduce to you, and I suppose many of you would already know Alexei Zheglov, who's an LKU, KCP, and AKT accredited Kanban trainer and Kanban certified professional, coaching professionals, I'm sorry. My name is Mahesh Singh. I'm a co-founder of Digite and responsible for product management at Digite Swift Kanban. Alexei has been in the field for a long time, brings a lot of experience to the table, lean product development and Kanban to intellectual organizations who seek modern management ideas and pragmatic guidance to improve high technology businesses. He's recognized as a Kanban coaching professional, and of course he's an accredited Kanban trainer. He's based in Waterloo, Canada, not too far from Toronto, and you can connect with him in multiple ways, and of course Alexei will talk a little bit more about that during his presentation. Before I hand over the microphone to him, a quick overview of Digite and Swift Kanban. So we've been around for over 10 years, and we are pioneer in the web-based collaborative products and solutions for, especially for geographically distributed teams. We're headquartered in Cupertino, California, in the Bay Area here. We have over 300,000 users across the world using our products, which cover Lean Kanban, Agile Application Lifecycle Management, and Project Portfolio Management. And of course, Swift Kanban is our flagship Lean Kanban product. It's been used by customers around the world in a variety of applications. Of course, the primary customers that we have are people who do software development, IT or DevOps, and use Swift Kanban in Kanban and Scrumban settings. But we also have a number of other applications of Swift Kanban in non-software, non-tech contexts, and we have customers using us for marketing, procurement, HR, and a bunch of other fields. And of course, we have a number of people using us for personal Kanban, whether it's planning your party or managing your kids' homework or personal chores and things like that. So there is a wide application of Swift Kanban. We provide some of the most extensive metrics and analytics on Kanban, and we have been recognized for our capabilities for these analytics as well as for our enterprise Kanban capabilities. And just to give you a quick sense of who are the kind of organizations that use our products, we have some very well-known brands and very large companies, global organizations, as well as very small companies using our products for their personal as well as obviously for the professional use within the context. So with that, I'm going to hand over this presentation to Alexei. And Alexei, a very warm welcome to you today on this webinar. And let me go ahead and make you the presenter. Okay, there you go.
Thank you very much, Mahesh. So first, a few words about myself. This is me. I'm sorry, let's go back one slide. So this is me. Mahesh has already introduced me. This is my contact information. The blog URL is connectedknowledge.com. There's also my company website, leana2z.com, my email address, and my very short Twitter handle, which you can use to refer to various things that I'm about to say. I have one small announcement to make. It's a training event that will take place in Toronto at the end of April. For our listeners in Canada and in the United States, within a reasonable flight distance from Toronto, this is a unique event that is modular, combines foundation and advanced classes. You can mix and match any custom program lasting from 2 to 5 days. And this is also a unique opportunity to earn a new credential introduced by Lean Kanban University this year, Kanban Management Professional. If you simply enter Toronto Kanban Week in Google, the registration page will come up on the first page in the search results. So after this quick announcement, let's jump into the very interesting topic of lead time. And I'd like to start it with a big disclaimer, known as Goodhart's Law. And I want to make sure that everything we talk about today kind of is said with this very deep thought in mind. Whenever we say that we measure something, that must include thinking about how our act of measuring will affect the system that is being measured, what response it may provoke, and how that can change the results. And after this disclaimer, let's revisit the very important definition of lead time. So here's a board that visualizes a Kanban system. So you can see several consecutive work in process limited columns. And the lead time spans 4 of these columns in this example. It's from the so-called the first commitment point. In this case, it's the very first of the limited columns, the input queue. This is the moment where the two sides come to an agreement that now is the right time to start working on something. And the lead time clock stops when the work item reaches the first infinite buffer. This is the state where the work item is now ready to deliver, and it's up to the customer when to take the delivery. Sometimes there is no infinite buffer at the end, there is just the customer. In that case, the lead time extends all the way to the end. Lead time can naturally be thought of as the time how long it will take to deliver something. But there are actually a couple of questions that we can replace this question with, and it's actually preferred. The two questions that I prefer are to ask, when will we need something, and when should we start working on it? So the two moments are key here. One is the desired delivery date, and the other one is the optimal start. And one of them simply leads another by this unknown amount of time. Why is that we have this kind of definition of lead time? There are several alternative definitions of lead time that you can find in lean literature. So let me give you a few reasons. Suppose we extended this definition and we kept the clock ticking until the customer actually takes delivery out of the ready-to-deliver buffer. In this case, we would include the time that the work item spends in this buffer. And what would that time depend on? It would depend on how frequently the customer takes the delivery. Imagine the situation that we have a similar delivery capability on the software team, but the feature may be delivered, let's say, to a website, which can happen several times a day, given modern technologies. And it is also delivered as a desktop application. And the desktop application may not actually make sense to maintain, update every day. So we'll have the same delivery capability in different sets of lead time data. So how frequently we take delivery largely depends on the economics of our relationship with the customer. On the other end of the system, if we included the time that the work item spends as an option, and the very leftmost column in this diagram is our backlog of ideas where everything is still an option, then a couple of undesirable things will happen. First of all, in most product development processes, there is a substantial degree of optionality. Some of the ideas will be discarded, like, for example, the backlog item C that has just been discarded and it will not be committed to. This will almost always ensure that one important forecasting tool, Little's Law, will never work. Even with the current lead time definition, it is not guaranteed that it will always work, but it will work sometimes. If we extend lead time definition to include the backlog time, it will never work. Another important point relates to Goodhart's law. One of the things we want to do in lean product development is to defer commitment. And if we include the amount of time the work item spent as an option, then we actually encourage the opposite, committing early. And this happens because most time metrics are treated by people naturally such that people like to minimize them. And we don't want to necessarily minimize that if we want to defer commitment. There's a couple of important metrics somewhat related to lead time. One of them is customer lead time. This is actually the metric that extends all the way to delivery. And we can model it as the system lead time, and we can model the time spent in the unlimited buffers, and that way we can get the total amount. And there is also the cycle time metric. But the important thing about cycle time is that we have to qualify where it is to and from, because there are several activities, and sometimes cycle time may span one activity, sometimes it may span a couple of activities or more, depending on why we're measuring this thing. Cycle time depends mainly on the size of a local effort, unlike the lead time that, as we'll soon find out, depends more on the systemic conditions in our Kanban system. After this webinar is over and you get the recording and the slides, I would like you to discuss this slide in your workplace. There's a number of good questions to ponder about gaming metrics. Particularly, I like the question number 3 here: how would you gain the local cycle time metric? Because cycle time is determined primarily by the local effort. We could gain this metric by dividing our work items into smaller work items. Of course, they would be completed faster, and that way we can demonstrate huge progress on this metric without actually improving anything in our system from the customer point of view. Lead time, unlike cycle time, turns out to be much more resistant to such gaming, and the reasons for that largely lie in the concept of flow efficiency. I assume most listeners to this webinar and Swift Kanban webinar regulars are very familiar with this concept, so I won't spend more than a minute on it. So essentially, we can model customer lead time as a sequence of red and green, where green is the touch time that we actually spend working on something, and red is the time the work waits. Sometimes it waits in explicit waiting states, and sometimes there are hidden queues due to multitasking. If we calculate and measure this average, it usually turns out to be between 1% and 5%, a very small number. If the flow efficiency is, for example, 5%, then it turns out that the improvement in local effort has a relatively small impact. But if we somehow manage to reduce those delays, the improvement can be much more substantial. And this makes lead time very hard to fudge. The lead time is not additive. It's not like if we have 5% flow efficiency, we just make every work item wait 19 minutes for every 1 minute of effort. It's not distributed evenly. Some work items don't wait at all. Some get delayed a lot. And this may depend on prioritization, it may depend on our scheduling policies, it may depend on simply random events. So we cannot simply take the red blocks out of the diagram and construct a leaner, more effective process out of green ones. We can only improve lead time if we create some system-level improvement. By the way, this slide discussion too is another set of questions that I'd like you to take to your workplace and discuss with your colleagues and managers. Lots of good discussions can come out of this. And I'd like to finish this section of the webinar about the definitions of lead time, cycle time, and so on with this corollary to Goodhart's law. Since we know that measuring something can provoke a certain response that can skew the results, we have to understand that we need to know where we're measuring the time from and to. And it's really important to know where the first commitment point is in our system. So if you're visualizing the process, whether you call it knowledge discovery process, value stream, workflow, or not, in the knowledge work Kanban system, the commitment point has to be very clear. Measuring lead time is really not that hard. I often see how various delivery teams have no trouble simply writing the start date and end date on a sticky note. Electronic systems handle this quite well. The difficult part is this. When we finally compile lead time data, and this is the example from one of the IT organizations, the inconvenient truth comes out. Lead time is not a number. It's a probability distribution. And another thing about it is that the Kanban systems typically deliver not homogeneous work item types. The demand placed upon our system is differentiated by type of work and risk. There's typically more than one type of work that each delivery team delivers. So if we look closely into this sample data set, actually it includes 4 different types of deliverables. They're all color-coded in the bottom diagram. And we can see different patterns, how, let's say, purple projects generally take much more time than the green ones, and so on. So if we drill down our lead time data set by the type of deliverable, we basically get 4 different distributions. So here's how it worked out in this example. And here's the important thing. We cannot communicate our capabilities to deliver if we only go by averages. So, for example, green projects take on average 30 days. What does it mean? That's simply not enough to manage the schedule risk. In order to manage the schedule risk, we need to know, for example, what's the probability that our delivery will exceed, let's say, 60 days or 90 days. In order to communicate that, we need at least one more number, and that's usually a high percentile, usually a number between 80 and 99%, depending on our tolerance of schedule risk. So remember to always include at least 2 numbers when communicating lead time and setting delivery expectations. Usually the average and the high percentile work very well. So here's another example, and this is data from a small software delivery group that juggles two types of work. One is the new feature development, and the other is what they call support. And what this really means is there is some defect uncovered in production that requires a code fix, so they rush to implement the code fix and push it to production. So we can see that there are two distinct shapes, distribution shapes here, and they are somewhat typical. Weibull distributions, so-called Weibull distributions from the Weibull family, occur quite frequently, and so here I'm giving examples of two fairly typical shapes. The one on the left has a shape parameter of about 1.25, quite common in product development. And the one on the right, operations support customer care type of work, typically have the shape parameter of around 1, which is known also as the exponential distributions. Occasionally I see that parameter go below 1. I don't want you to really get hung up on the mathematics of it. Like remember these terms. The really important thing here is to see the symmetry of the shape of this distribution curve. Time is naturally asymmetric. There is a brick wall essentially on the left because the delivery time cannot be less than 0. But there is such a wall on the right, and so there is this long fat tail that extends to infinity. So the peak of the distribution is usually very much less, and then there is very gradual descent into this long tail. And that's the most important thing to remember about distribution, this notion of asymmetry. If you do the best fit curve matching, you can find the parameter for your process, and that typically forms its unique signature. Because of the distribution curve asymmetry, I like to see it kind of in different colors. So I created this rainbow model that kind of brings, kind of makes the boring bar chart much more interesting. It's because different points on the distribution curve play very distinct roles. So let's go through these 6 roles. So I'll start with the mode, which is the peak, the left-shifted peak of the distribution curve. So this is the typical delivered work item. This is how we remember it. The trouble is that in most typical lead time distributions that we see from product development teams, it's very much left shifted and it falls on a very low percentile, typically around 20 to 30%. So the danger here is that you can ask someone the question, how long does it typically take? And they give you a pretty good answer. The problem is things will, with a probability of 70 or 80%, take longer than that. And the answer will still be accurate. So that's the danger that we have to be aware of when dealing with probabilistic lead time. The median, which means over-under, basically, 50% of work items will take less time to deliver, 50% will take longer. This is the perfect thing for creating very short feedback loops. Those listeners who have read the Blue Book by David Anderson that came out in 2010, and remember the story of Kanban implementation in Corbis. So there is one part of that story that didn't fit into the book. And that part was about creating very short feedback loops based on the median. So if you can scale the distribution curve that I'm showing you on the screen right now, such that the median is about 2 days, and basically the maximum lead time for a user story in a large project is about 10 days, then it turns out that all user stories, when they are delivered, can be sorted into two piles, the one that took up to 2 days and the ones that took longer. And if these two piles are equal, that means the project forecast is on track. It's accurate and the project is on track. And if, let's say, the pile of longer lead times start growing, that means the project is off track. And the beauty of it is that the median occurs very much on the left side of the distribution. So it occurs early. That means we know early if our project is still on track or getting off track. The average lead time is, of course, needed for Little's law, which connects three important variables: the average amount of work in progress, the average lead time, and the average delivery rate. And Little's law, of course, comes with a disclaimer. It has to be handled with care. The 63rd percentile is the best indicator of the scale of the lead time in our process. The high percentiles, as I already said, are critical to defining service level expectations. And they also play an important role in Kanban cadences. At the replenishment meeting, we can use the current service level expectations to decide is now the optimal time to start working on this or that or that. And in two other important Kanban cadences, we can actually review the existing lead time distribution and see what we can do about it. So risk review, which was pioneered by Klaus Leopold, focuses on trimming the tail of the distribution by going after the causes that cause those massive delays. And that typically results in left shifting the whole distribution curve. And finally, if you must use statistical process control, not that you have to, then you can figure out the control limit, and I've seen how this helps, for example, teams that use iterative methods. For example, if the right hand side of this diagram corresponds roughly to their sprint duration, that means their typical user story has to be about 1/10, maybe to 1/5 of that. Setting SLAs in operations can also be done using this. So, for example, I met with one of the operations managers this morning, where they set the SLAs as approximately 20 times the average delivery time. That's because they have a very long tail on their distribution. So that's how they figured out their control limit, and so on. There are several so-called reference distributions, relatively frequently occurring shapes, and with a little practice, you can almost always match the given histograms of lead times to one of these 6 shapes. So this is something that I'm still working on, and I plan to release it, the set of these cards with instructions for training and education purposes. And I also wanted to bring to your attention this very interesting distribution. Very often when we talk about knowledge work, we really mean something like software development or IT, where almost all the work happens inside people's brains. And the mechanistic standard work is almost negligible. Of course, people in IT can very easily understand this because, well, standard work is typically things like compilation or copying files. That happens very quickly, whereas the knowledge work is actually creating code and clarifying requirements, and that takes far more time. So the amount of standard work in let's say, software development is almost zero relative to the lead time. However, this example comes not from software development, but from another intellectual field, biotechnology. I cannot tell you what exactly is happening here for confidentiality reasons, but you can imagine that this is a series of experiments where scientists, such as biochemists and geneticists, grow something in petri dishes, and then they test something, and then they run another experiment, and they eventually interpret results, and that feeds into a larger drug development program. So the first lead time data set that I got out of this type of environment, and it has relatively few data points, but it has two very interesting features. First, there is a non-negligible amount of standard work. It's shown on the left. It's about 3 days of fixed time. Well, you have to give their lab equipment some time to run, and this is the minimum time any experiment will take. And then the curve on the right represents the familiar intellectual work that is variable and unpredictable. So in situations where the standard work takes a non-negligible amount of time, the translated distributions can help us model this effect. Also, while I was preparing an earlier version of this presentation, it actually happened last fall when an unfortunate epidemic was raging in Africa and making world news. So David sent me this picture from The Economist magazine. Well, this is actually Weibull distribution with shape parameter 1.9. Very interesting. It turns out that the processes of a group of people collaboratively breaking down, solving a problem, and delivering the results is statistically not too different from, let's say, viruses defeating the antibodies in the human organism. Very interesting. So statistically, these very different phenomena are described by very similar equations. So another discussion point, and I'd like you to take this to your workplace, and the biggest question here is that, is your organization ready to face the inconvenient truth that the work that we do, the results that we deliver, are essentially probabilistic and not deterministic? Are they ready to face it, or, you know, we will pretend that it's deterministic and simply ask questions like, give me a number? And the final section of my webinar, still related to the lead time, will contain a few words about projects. By the way, I don't mean to pretend that I'm a big fan of, let's say, very long projects, but sometimes it just happens that this is the way we do business. And in Kanban, we start with what we do now, and we don't judge the existing processes. So we have to figure out how to model large batch deliveries. So this is basically how a Kanban system can model this delivery. You see the infinite buffer at the end of the Kanban system. This is where a number of features gather, and then we create a large batch out of them, and then we deliver all of them at once. So this is basically how projects work. So in order to use our knowledge of lead time to plan and manage such delivery, we have to use Little's law twice, not once but twice. So the first time we use it, we have to figure out the delivery rate. So the trick with Little's law is to see which of these three variables is a fixed variable, which one we can vary, and which one is the output. So here, we can treat the batch size as more or less fixed. We know the set of requirements. We can estimate the size of our delivery in terms of the number of features. And here I recommend the work of Dimitar Bakarjiev on probabilistic project sizing, where he describes statistical sampling techniques which are remarkably accurate and help us figure out how many lower-level deliverables, such as features, the project will consist of. So we start with that. We can consider a project duration. So let's say 6 months. We divide one into another, and we get the delivery rate. So that's really as simple as that. So if, let's say, we currently measured the proposed scope of the project as 600 features, and our project proposed project duration is 6 months, then we need the delivery rate of 100 features per month. If we're planning this as a 12-month project, then our delivery rate should be 50 features per month. If it's a 3-month project, then it should be 200 features per month. And then we use Little's law once again, but now our delivery rate is kind of plays a different role, so it's our target that we need to hit. And the lead time can be treated as a fixed variable, but we know from our lead time distributions, right? Because we kept those metrics from the Kanban system. And here, if we multiply the average lead time by the average delivery rate, that gives us the number of features that have to be in process simultaneously at all times. And that determines our staffing level because, well, when we measured our lead time, we were, let's say, working on average, let's say, 2 user stories per staff member. Well, that means our WIP will translate into a staffing level for the future project in roughly the same proportion. Well, it sounds simple enough, but there are 2 big elephants in the project planning room. And if you have any doubts about the sampling techniques that you can read in more detail in Dimitar's paper, there is, of course, some sampling error. But this error will be dwarfed by the 2 elephants that I'm about to introduce you to. So the first elephant is the dark matter. If we think our project has 600 features in it right now, well, that number will probably change. When some of the features will meet the customer or some customer liaison, product owner, and so on, and when we'll get some feedback, there will be emergent requirements. We'll see that the actual count of features will increase. Some of the requirements are subject to change. There is some non-trivial probability that they will change. And if the project lasts long enough, some of those risks will materialize. And by the way, all of this can happen without any scope creep. No requirements actually added to the original scope. The amount of dark matter will be large or small depending on how well the problem domain is understood. If it's not understood very well, expect more dark matter. If our risk management practices are more mature, then we'll get the work, we can hope to get the work in the right order to minimize changing requirements. As for the actual data on dark matter expansion, actually I'm again referring to the same article by Dimitar, and it also includes a contribution by A.J. Reddy, which will, by the way, make it into his next upcoming book on Scrumban. So the data shows that sometimes dark matter is negligible, and sometimes it exceeds 100%, which effectively more than doubles the scope. And the percentages from 20 to 70 are quite common. So this will clearly be a much bigger problem to deal with than a sampling error in estimating any project scope. All right, well, the second elephant in the room is the so-called Z-curve effect. And what this refers to is that if we were to plot a cumulative flow diagram of feature delivery within a project, it doesn't follow a straight line. It looks like an S or a Z curve where the delivery rate is faster in the middle and slower, let's say in the first approximately 20% of the project, and it also slower in the final stretch of the project. There is a number of reasons why things are going slowly at the start and why they tend to slow down at the end. Partly because it takes some time to deliver first few features. It takes time for them to travel the length of the Kanban system and reach the delivery buffer. It may also be due to the fact that some of the technically risky but must-have from business point of view requirements tend to be prioritized earlier and they actually take longer. And at the end, we have already accumulated a fairly large batch of features and some integration issues that tend to slow down the process a little bit. But if we do the math and use, let's say, a 3 to 5 to 1 ratio of the slope of the delivery rate in the middle, to how it is at the start and at the end, then actually the required delivery rate that we have to sustain for the middle 50 to 60% of the project is about 40 to 50% greater than the delivery rate, the average delivery rate for the project. So if, let's say, we have a scope of 600 features and we're planning a 6-month project, then the required delivery rate that we actually need is not 100 features per month. It's more like 140 to 150. And that will also be much a bigger factor than any sampling error when handling the project scope estimation. So for project managers, the project initiation phase creates a huge opportunity to create a useful forecasting model for the project, which can be done by sampling requirements and coming up with a feature count, then dealing with the project room elephants to get the realistic delivery rate that we need to attain in the middle of a project, and translate that into the required capacity using our lead time metrics. And after that, build the feedback loops using the properties of the lead time distribution curve for the features. These feedback loops will help during the project execution. They will inform us very quickly if our project is still on track, if our project is slowing down and getting in trouble, or perhaps we've realized some process improvement which is actually speeding up the delivery and buying us the margin of safety when dealing with the schedule risk. And steps 2 and 3 could be done more than once. We can plan the project, we can create multiple forecasting models for different start times, and that could give us some options to hit the optimal start time. So the summary of project initiation is: don't waste time on deterministic planning, create forecasting models and feedback loops, possibly even more than one model, and let's not forget what the must-haves, the table stakes type capabilities are needed for this. We need lead time data, we need to somehow measure it, and what this basically means is we have to be proficient with the Kanban method at the feature level. Approaching the conclusion of our presentation, I'd like to thank a number of long-time senior Kanban community members that I learned lots of things from, and without them, the discovery of things that I'm presenting here today would simply not be possible. So here they are. You probably recognize many of these names. And this is it, my contact information at the end, and the reminder of the upcoming training event, Kanban training event in Toronto. And I would like to turn it over to Mahesh to follow through with questions and answers.
Thanks, Alexei. I'm going to actually keep you the presenter because I think in case people want to see any of your slides. So let's have Alexei still as the presenter just in case we need to do that. So a number of questions have come in, Alexei, and I'll encourage other attendees to ask any questions that you might have on the presentation that Alexei just did. Fascinating presentation, especially in the context of how we see so many of our customers sort of follow the traditional methods of project estimation, project forecasting, or project delivery forecasting, and so forth. So in that context, there are a number, a couple of questions that I have. But let me start with some of the sort of one of the basic questions that a lot of our customers who are just starting their Kanban journey, they ask. Which is, what is, there is a lot of discussion that happened some time back, and I'm not sure that it happens anymore, is what is the difference between lead time and cycle time? And you did lay out a number of sort of segments of the, overall delivery time that you showed in the slides, Alexei. But could you talk a little bit about, what is the right terminology these days? Is it lead time or is it cycle time? Is it both?
We have both terms, and of course we can measure both. The important difference is that lead time in the service delivery Kanban system is an indicator of some systemic condition. We cannot improve it in a meaningful way without some improvement of the system. Whereas the cycle time is a metric that can actually be changed quite significantly by implementing only local changes. And that's the main difference. This doesn't mean that one of them is necessarily superior to another, and I've seen some teams track their local cycle time, and it helps them understand their process better. The important thing is they knew what they were doing, why they were doing it, and it helped them. Lead time is, of course, more important in terms of forecasting deliveries and establishing service level expectations and establishing the delivery predictability for our service delivery Kanban system.
Got it. Got it. The other question that I had was on something that you mentioned towards the end, and that is the need for having lead time data in order to be able to build the forecasting models, and that's a question that is also coming from Jason Ives. So how much lead time data do you need before you can use it for building a project forecasting model?
So usually not much. In my experience, and of course Troy McGinnis deserves a mention here in a big way. It's the number is it may be as small as a dozen. So 10 to 30 data points, most recent deliverables, is enough to understand the shape of the distribution. And establish some delivery expectations. So we don't need to collect giant data sets in order to realistically forecast our deliveries.
Right, right. And now this, when you say that you need that set of data, you need it for the team that's under consideration, for the team, for the project that's for which you're trying to build that model, correct? Because one of the sort of big challenges that a lot of our consulting customers or IT services companies face is that they are required to submit a fixed bid with a fixed cost and timeline, and obviously their team hasn't even they may not even have assembled a team many times, and they even if they have assembled the team hasn't yet started to work. So it becomes very hard for them to get any kind of real data about the team that's going to actually work on the project. So in such cases, obviously, how do you do something like that?
Okay, so in this situation, it's important to realize one of the implications of relatively low flow efficiency. So the personnel changes to the team have a relatively small effect on lead time, because the systemic conditions which cause the delays, which are 90+% of the lead time, still persist from one project to the next. So to a significant degree, the feature level lead time from the previous project will retain significant amount of validity for the future project going forward. So if you have feature level lead time data from your recently completed projects, it is quite likely that you can use it for the next project, and also you can build in feedback loops that will let you know very quickly, very early in your next project, if if your project forecasting model was realistic or not.
Right, got it. There's a follow-up question on this from Steve McGee, and his point is that even with the 10 to 30 data points, what if there is noise early on in your data, like people interrupted to finish previous work, etc.?
Well, the answer here may depend. So one thing here is that well, we all get interrupted, and that's part of the system. We don't work 100% of the time on one work item type, and that's one of the reasons why there are delays and why we get these lead time distributions that we see from many teams. So one possible answer here is to use the realistic data, how things actually are. One nuance to this answer could be that if Steve sees some very unique events that were happening at a certain time of the year that skewed the distribution, so it no longer really represents the system, then we have to make some adjustments to the data set and perhaps discard some of the data and go by some other data set that they may have. So the important thing is to have a data set that realistically represents the delivery capability of the team, that is relatively recent, that does not assume any future process improvements, and is basically free of noise due to one-time events.
Noise, right. You have some data cleaner that might be needed. Another question is from our CTO, Dr. Ramesh Patel. He's also on the call here listening to you. And his question was related to the project estimation slide that he showed. And his point is, can you elaborate on how we can estimate the staffing size based on the WIP in the project planning? Given that most of the WIP is, a lot of times the WIP is really waiting time.
Right. So the relationship is this: we can. When we were running our previous project or our recent feature deliveries, we had some process in place, and one of the explicit policies of that process was basically how much work in process we have. And under the constraint of that policy, we collected this lead time data set that shows that our average lead time is this much. And we know how many people work there, so we know roughly the relationship between the WIP limit that we had and the number of people we had. For the next project forecast, we use roughly the same ratio to translate the amount of work in progress into the staffing level.
Right. Okay.
So if okay, so let me give you an example. So if let's say we had let's say a total WIP limit for all the work in process, let's say 40, and our usual policy was approximately on average 2 work items per worker on the team. So we have a team of 20 workers, and they handle on average 40 concurrent work items. And so in the process that looks like this, we compiled our lead time data set, and when starting the next project, we created a forecasting model based on it. And that forecasting model says that, let's say we need 30 units of WIP. That's our needed capacity, and that would translate into the staff requirement of 15 people to carry out the project according to the model.
Right. Right. Got it. Another question that I think that a number of people might have on this presentation today is come from Richard Paul. When talking about the shapes of curves, the numbers that you showed against each shape, 1.62, 3.22, etc., how are those values calculated? You might want to explain.
So those the formulas are all well known, and they're all calculated from them. So these are all well known, well studied distributions.
Okay, got it. Couple of questions. One is, how realistic, this is from Nadia Talat. Nadia, welcome to the webinar. How realistic is this way of using this law twice to come up with the target of people and delivery rate? And I guess this is a follow-up on the same thing. Isn't the delivery rate a function of system of work, which includes the people and policies?
Yes, it is a function of the system of work, and we have yes, exactly. In in the model that I presented, we actually use some facts about the system of work, such as the CFD that doesn't follow the straight line, which causes this upward adjustment of the delivery rate. We also the current state of the system of work manifests in the emergent requirements, in how much of the requirement change risk will materialize. And all of these things happen to a greater or lesser degree depending on how on what our scheduling and sequencing policies are.
All right. Another question that came from Steve McGee is, I understand, and I think you mentioned that as part of your differentiation between different work types when you're doing the overall distribution curve, is that there is no need, I understand there is no need to have work items by similar size. Can you explain why this is true?
My take on sizing work items is that it has to take flow efficiency into account. If so, we can definitely have work items that sometimes the biggest one is much bigger than the smallest one. Whether this size difference is meaningful for the purposes of planning and estimation depends on flow efficiency. If our flow efficiency was very high, then the gap between the size categories has to be smaller. And when the flow efficiency is low, then size matters less.
Got it. Got it. Looks like we are coming up to the top of the hour. In fact, we are at 11 o'clock. So I'd like to have a last quick question, and that is about your class schedule, especially here in the Bay Area. So question from Javier Bonames, our old friend. When are you having a KMP class in the Bay Area?
All right, so why not have it in the Bay Area? I think Javier and I could discuss it offline, and if there is interest, we could schedule a program like this um, in the Bay Area at a later time, perhaps in the summer.
Absolutely, good time
I
to
see why
come.
not.
This sun is shining bright outside my window here, so summer has already started here, Alexei. I don't know how it is in your neck of the woods.
Okay.
All right, and Steve says that there is interest. He says we can invite people to the class. So so certainly there is interest. We should talk about that, Alexei. We should initiate that conversation with Javier and Steve, I suppose.
Okay, we'll follow up. Thank you.
Wonderful. Alexei, thanks so much for the webinar and for the very interesting and I think very uh, practical and directly usable talk because I think everybody who's sort of early or even reasonably advanced in their implementation of Kanban for a variety of work uh, have all of these questions and would benefit from some of the questions that are put to them by their managements. In terms of being able to adopt Kanban successfully for, forecasting, for, establishing a far better set of practices than what they might currently have, where there is dependency on, making early estimates that, in any case, can't be kept later on. So, thanks, for the wonderful talk. Any final words from your side?
No, well, other than Mahesh, thank you very much for the opportunity to present this webinar and inviting me here.
Wonderful. And also thanks very much to all of the attendees today. Really great set of questions and a good discussion towards at the end of the webinar. And we hope to see you again in a future webinar soon. In April, we plan to have the second in the series of our webinars with David Anderson on the Kanban for enterprise services planning. So we hope you'll join us there. And we will continue to announce webinars the rest of the year. And hope to see you and others in these webinars. Alexei, thanks very much again, and have a wonderful rest of the day. Bye-bye.
Thank you.